Okay, you are welcome to this tutorial. So today I'd like to go over like previous lessons that I've done and I've posted on the Telegram group. But first of all, what we want to treat today is mainly about solar panels. Okay, solar panels. So but before we do that, I would like to go over the type of connections that we have done before. So then the two main type of connections that we have, number one is what is parallel connection. Then the number two is series connection. Here we are going to break it down so that we understand what we mean by what parallel connection. So when you hear something like parallel connection, it means check if it's recording well. So when you hear something like parallel connection, what it simply means is, or in parallel connection, the voltage of whatever you want to parallel remains the same, but the capacity increases. Okay, for an instant, give me one cell, just a single cell. Now this particular cell, this is a 18650, is a 3.7 volt lithium ion cell. Okay, now let's check the voltage and see how many volts it is. 3.7 volts is just the nominal voltage, that is not the full voltage. Okay, so if you look at this, you have 3.3 volts. That is just the state of charge of this particular cell, is what 3.3 volts. But this cell is known as 3.7 volt lithium ion cell. Wherever you go in the world and you ask of 3.7 volt lithium ion cell, they will give you something similar to this. It may be larger or it may be in different shape or and sizes, but the main thing is to have that voltage as 3.7 volts. Okay, so now in parallel connection, just as you can see here you can see that the two positive sides, they are joined together using this nickel strip. Look at the negative side, the two sides, they are joined together using nickel strip. If I had two of these cells joined together, that separately, this is reading 3.7 volts and the other one is reading 3.7 volts. You know that if I join them positive to positive, then negative to negative, we are still going to have 3.7 volts. Okay, we're still going to have 3.7 volts. But now the capacity of this is 2.6 amps or 2600 milliamp hour, 2600 milliamp hour, or which is equivalent to 2.6 amp hour. Okay, if I have 2.6 here, I have 2.6 here, and I have joined them in parallel, it means that these two cells have become one battery, and then the capacity would now be 2.6 plus 2.6, giving us what 5.2 amp hour or 5200 milliamp hour. Okay, so that is for parallel connection. Now I can decide to increase these cells, that is to just be adding depending on the capacity that I want to achieve. Assuming what you want to achieve is 26,000 mAh. Now you will now say, okay, since each one of these is 2.6 amps, and then what you want to achieve is what 26,000 mAh. You will now ask yourself, how many of 2.6 or 2600 mAh can I get out of 26,000 mAh? So you have what 10 pieces of 2600 mAh cells, meaning that we need 10 of these to achieve what? 26,000 mAh. So here this particular one is also joined in parallel. You can see them. Then here this is also joined in parallel. We can now merge them together. Here we have 9 pieces. This is not up to 26,000 mAh. We need to add one more. Give me one more there. We need to add one more to get our 26,000 mAh. Okay, we need to add one more. Look at it. Assuming this is now joined together, you can see these are the positive sides. So if you are using a nickel strip, we are going to weld all this together and weld all this together. The voltages will become the same thing, but the capacity has increased. Okay, the capacity has increased. For an instance, if this we can use it for our, let's say, cell phone for one day. Okay, this is 2600 mAh. You can use it for a cell phone one day, and then someone tells you, I want a battery that can take my cell phone for about 10 days. What does that tell you? You just multiply that each cell. Now you will say 1 day is equal to 1 cell, and 10 days is equal to how many cells? Meaning that you say 1 cell multiplied by 10 days, meaning that you need what? 10 pieces of cells to achieve that capacity. So anytime that someone asks you, I want something that can power this, first things you ask is what voltage am I going to use? Once you get the voltage, then you will now derive the capacity of the battery that you need, that can take that load for the length of hours that the person wants. Okay, so this is a simple parallel connection. I think let's check the voltage of this battery now and see if there is any difference. Now this one is at 3.43. Okay, that is the voltage of this particular one. Then you can see that it's not up to, now the full voltage is what? 4.2 volts, and the low voltage, that is the lowest is supposed to go, is what? 2.5 volts. At 2.5 volts, your cell is considered to have zero capacity. Okay, now you can see that this is not even up to 4 volts. Even if it's up to 4 volts, or let's say it's up to 4.2 volts, it's still okay, because that is the full voltage. But assuming that this particular battery, we now use our multimeter to check it, and we are seeing 6 point something, or 7 points, or 8 points, we should know that that battery pack is not in parallel. For example, even if there is parallel connection there, series connection has happened, because no single cell can give you 8 volts or 7 volts. Okay, so that is it. Now if you look at this, though this battery is not done yet, someone is building this. If you look at this, you will see that all the negative sides here, they are joined in what? Parallel. All the negative sides, they are joined together. All the negative sides here, they are joined together. And when you come to the positive side, all these sides, they are joined together. Okay, this work is still a rough work. He has not finished doing the work, but that is just to tell you that in parallel connection, you can see all the positive come together. They are coming together to do what? To be able to withstand the load for a longer period of time. So that is it about parallel connection. To give another analogy, assuming that you have a tank of water here, you have another tank of water, the water is filled to the brim. Now in parallel connection, now this tank now will be joined, let's assume will be joined to this tank, to the second one. They have now become one giant tank of water. If you on this tap here, do you know that the water level in this tank and the water level in this tank, they will become the same thing? Because as water is flowing from here coming down, here will not be fuller than this one. Everything will be going down at the same time. That is parallel connection. Everything will be going down at the same time. Okay, that is what we mean by parallel connection, meaning that whatever the content that is in the battery will, you know, all of them will go down at the same time. And you know that if one tank is supplying the water, and let's say, okay, if it was one tank that is supplying the water, it may take about, let's assume 3 hours to completely discharge the water in one tank. If you now connect it to the second tank of the same size, it means that it will take about 6 hours. So that is simple thing about parallel connection. Then now we go to series connection. Okay, we go to series connection. Now we know what parallel is. Now in series connection, what happens in series connection? In series connection, the voltage does what? Increases while the current remains the same. Okay, the voltage increases while the current remains the same. So now I will just give us an analogy of this series connection. You know, the more voltage you have, the faster currents can travel. Okay, so now we have this 3.7. You know it's in parallel connection. Okay, here also is 3.7. This is also what? 3.7 volts. In series connection now, you connect the positive to the negative. Okay, meaning you have one open point here. Here will now be your 0 volts, or that is your minus. Then this place now is your first series. You connect this positive to the negative of this one. Once you connect that, I hope you know that the current of this battery is still the same thing. The current has not changed. Okay, these two batteries will now be working together. The current has not changed, but the voltage has increased. When they say voltage, it's just pressure. The pressure has increased. Okay, now let's check this. You have 3.286. Let's check this. We have 3.43. Now if we join these two battery in series, what are we going to have now? We have 6.72. So we have now joined these batteries in series, meaning the voltage has increased but the current still remains the same. There are so many appliances that if you don't use higher voltage for, it can never work. So if you want to achieve that voltage, what you do is what you do: series connection. After achieving the voltage of that appliances can work with, you will now talk of, okay, how many cells do I need to parallel to power that appliances for so and so hours. For example, now let's assume that we have a table fan that can run on 7.4 volts. 7.4 volts, meaning two of these in series. You know, it's 3.7, giving us what? 7.4 volts. That is a 2S battery. This is a 2S battery, assuming we have joined them together. So now you will now say, okay, since what we have here is what? 2.6 amps, 2.6 amps, 2.6 amps, giving us what? That is 2.6. Yeah, that is 7,800 mAh. So if we have 7,800 mAh here is also 7,800 mAh here. You will now say, okay, see if this can power my fan for, assuming 1 hour. Okay, you know the voltage is 7.4 volts. You will now say, okay, I want to power this fan for like 5 hours. Okay, what then do you do? it means that already you have achieved your voltage. What's remaining for you now is to achieve the current requirement. If this can take your fan for 5 hours, you will now say what? This three piece of cells multiplied by 5. Okay, that is 7,800 mAh multiplied by 5. That is what can take your fan for 5 hours. Meaning that you have one of these, another one, that is, you have to put, let's assume that these are three cells. You have to make them to be, that is like this, into what? 5 places, meaning that you need 15 cells to achieve that particular current that you need. I hope it's understood. Do you understand? If you don't understand, tell me, I'll go over it again. You don't understand? What don't you understand here? So that I will explain more.
The hours, like the time going.
Okay, now we assume that the fan we are going to use, takes 7.4 volts, meaning we have 3.7 volts battery. We have 3.7 volt battery. We series them to now have what? 7.4 volts. And then the capacity will be 2.6 multiplied by 3, giving us what? 7,800 mAh. If this particular battery now can power that fan for about 1 hour, for example, then you now say, how many hours do you want this fan to run? Someone will say, okay, I want my fan to run for 5 hours. Okay, what that means is that since this is what can power the fan for 1 hour, you need 5 of these to be able to power that fan for what? For 5 hours. Okay, and you know that whatever you put in the first parallel group, that's what you are going to have in this second parallel group. If you now say, okay, let me use 12 pieces here and use 15 here, definitely you know that the one with lower capacity will run down faster than the one with higher capacity. There is no two ways about it. If you do good, you see good. If you do bad, you see bad. Okay, so now what we now need is 5 of these and then 5 of these, meaning we need 30 pieces of these cells. We have 15 here, we have 15 here. We will now do what? Series them. That is what is going to power that fan for what? 5 hours. Or if you are driving in a car, you now say, okay, I want 1 liter can take me for 1 hour on this car. You now say, okay, I want to travel for 5 hours. If 1 liter can take you for 5 hours, then 10 liters should take you for how many hours? Meaning what? 50 hours. That is what the simple calculation here. There is nothing more. Okay, so when you want to power an appliance, first do your what? Know the voltage that it requires. Then you now talk about the current need. So now let's go to what I wanted us to discuss today. So I wanted us to say something about what? Solar panels. Okay, I want us to say something about solar panels. We are not going to go in depth, but we do some practical so that we understand what we are saying. Now, solar panels, they are made up of solar cells. Let me just draw something. I know you understand this. So these solar cells, once you expose them to light or to sunlight, they generate what? They generate current. Okay, once you just keep, even as this is here, that the sunlight is just shining on, it's generating something. Okay, so now this is a solar panel made up of solar cells. Okay, these solar cells, they are joined in same series or parallel connection to achieve a certain voltage and certain current. So you see, before you go into anything, you must know your connection, the type of connections. So the way you look at them, they are arranged in series and also parallel to be able to achieve a certain voltage. So now, for every solar panel, it has what? Something like nominal voltage, okay? Then we have some that they are called 18 volt panels. 18 volt, meaning that, okay, 18 volt panel. Then the VOC, open circuit voltage. What this means is when you hear open circuit voltage of a panel, it means when that panel is not connected to any let's say charge controller, or is not working. Okay, what is the voltage that panel brings out? Most of these panels, you see that they bring out about 22 to 25 volts. Okay, this is the VOC. But immediately you connect it to charge controller that has a battery already, this voltage will drop. It will come to what? 18 volts. That is the voltage that I use in charging that battery. And you should know that if you have 18 volts, definitely the battery should be what? 12 volts, because 18 volt panel cannot charge a 24 volt panel. Why? It's only higher voltage that can give a lower voltage. Okay, 18 volt panel cannot charge a 24 volt battery unless you are stepping up that voltage. Okay, unless you are stepping up that voltage. So wherever you have a 12 volts battery, your panel should be at least 18 volts to be able to charge this 12 volt battery. Okay, to be able to charge this 12 volt battery. So that is it. 12 volt battery, you should have at least 18 volt panel. So now let's assume that this panel is 180 watts. That is 18 volt, 280 watts. Automatically the current will be, because power is equal to voltage multiplied by what? Current. So the power is measured in watts, voltage is V, then current is amperes. Okay, so you now say power is 180 watts equal to the voltage is what? 18 volts. Current is not known. Abi? Current is not known. We now divide here with 18 volts, divide here with 18 volts. This will cancel out this. Then 180 divided by 18. 180 divided by 18, it will give you 10 amps. So current will be what? 10 amps. That will be so this panel now that is 180 watts, 18 volts, which will now be rated 10 amps panel. Okay, the current will now be 10 amps. So you can find this information behind your solar panels. You can find it behind your solar panels. Now there are some panels that you can see they will write 36 volts, 36 volt panel, assuming let's say 360 watts. Looking at this, can someone tell me what the current will be? The panel is 36 volts, then the wattage is 360 watts. What would the current be using this formula that we have used here? Okay, they say 10 amps. So this is quite self-explanatory. We just say 360 divided by the voltage, which is 36 volts, will now give you what? 10 amps. Okay, so that is that when it comes to power. So now assuming, let's say you have a 12 volt battery now that you want to charge. Okay, and definitely you know that once you have your solar panels, the next thing you need is what? Solar charge controller. Then before your what? Your battery. These are like the basic things that you need. Then from your battery now, you now have your what? Your inverter. Now solar panel, solar charge controller, then your battery. Now before you couple this system, or before you build this system, you already know let's assume that your battery is 100 amp hour. Then your solar charge controller is this. You ask yourself, this system that I'm building, what type of solar charge controller should I use for this system? Some will say use PWM, some will say use MPPT. Now PWM, they have already said it. PWM is it's just like a switch that once it opens, the battery will charge. Once the battery is fully charged, it will just close. Okay. PWM charge controller, if you are using a 12 volt battery, I advise that use PWM charge controller. If you are using a PWM charge controller, your solar panel should be as close as possible to the voltage of your battery. Why? It's because your PWM charge controller, it cannot convert voltage to current like MPPT. I don't know if you understand. It cannot convert voltage into current like MPPT, because in MPPT you can use a 36 volt panel for a 12 volt battery. Your MPPT will do what? It will reduce this voltage and then what? Increase the current output. It will reduce the voltage and give you what? And increase the current output. If you are using a 36 volt panel for a PWM charge controller and your battery is 12 volts, assuming that this is 36 volts, 10 amps, that is what it's producing. If your PWM should give you, assuming if it can give you 9 amps out of these 10 amps, your battery will now be charging at 9 amps, and you know that the voltage is high but the current is low. Okay. Let me come again. Now your panel is 36 volts and then the rated current is what? Is 10 amps. Okay, is this ringing? 36 volts, 10 amps. 36 multiplied by 10 is what? 360, abi? Yeah. 360 watts. Then you have another panel that is 18 volts, 10 amps. 18 multiplied by 10, 180 watts. Now I have a 12 volts battery. I have a PWM charge controller. Then I have 360 watts panel that is giving us 10 amps. And also have 180 watt panel of 10 amps. Now you would agree with me that if I connect this 180 watt panel to this PWM charge controller that cannot reduce voltage, this battery will charge fine. Abi, assuming that the PWM charge controller gives us, or let's assume it gives us 8 amps out of this 10 amps. Okay, we are still okay. But now if you go and use 360 watts panel on this PWM charge controller to charge a 12 volts battery, what will happen? This PWM may give you only 8 amps out of these 10 amps. The excess voltage that you have, of which this one is 36 volts, the excess voltage is a waste because PWM cannot convert that voltage into current. I'll show us an example of MPPT here, how it works. It cannot do what? It cannot give us more power. This will now be giving us like half of this 360 watt, which is what? 180 watts. Okay, but if you have a 24 volts battery and you are using PWM, and then the solar panel is 36 volts, 360 watts, let's say 10 amps, what will happen here is that your 24 volt battery, you can see that it's close to 36 volts. More than 12 is close to 36 volts, right? Yeah. So only this 36 volt panel can charge that is this 36-volt panel now, it can charge a 24-volt battery. Because the voltage difference is not much, this PWM can give you, it will give you current that is close to, let's just say, the maximum current that it can give you. It will not be more than 10 amps. We know that already. But if it were a 12-volt battery, you use 36-volt panel, it will give you like half of the power that this panel is generating. So this will now help you to determine, should I use PWM or should I use MPPT? I know there are different advantages to using PWM or MPPT. Like in PWM is more cost efficient, it's not as costly as MPPT. But in a situation whereby you can afford the MPPT, then, and your battery is 12 volts and your solar panel is 36 volts, 10 amps, this MPPT will try as much as possible to this charge controller will try as much as possible to do what? To supply 10 amps to your battery pack. So I want to show us an example on this hybrid inverter. So now what we have here is solar hybrid inverter. It has an inbuilt MPPT charge controller. Okay, because it has an inbuilt MPPT charge controller, the solar panels that I use, I did more of series connection, so I achieved a higher voltage, okay, with little current. So once the voltage gets here, the MPPT that is in here will now do what? Step down that voltage and then give me more current. Now the sun is not much, but you can see here what you have is what? 70 something volt or 70 volt. The current is still at 5.6 amp. The sun is not that shiny, but if I had a PWM, I will not be generating up to this amperage at this time. Okay, why? Because the voltage is way above the voltage of my battery system. So these are like the two main difference that you look out for your PWM MPPT charge controller before you use any of them. So if you like this video so far, give me a thumbs up and also subscribe for more. Thank you.